compression. Number one, you got to solve this truss. You're given cross-sectional areas for each one. You're given material properties. Calculate the stress tensor, maximum shear stress. Okay. And I'm going to call it members 1, 2, 3, A, B, C for the joints. So I'll start with A. So here's the pin. We have a force F1 there, a force F2 here. And then there's also the force that's applied to that pin by the ground. So I'll put that in like this, and that's RA. This is equilateral, I think, in 1 meter. So Newton's second law says RAX, RAY plus 0.5 F1, 0.866 F1 plus F2, 0 is equal to zeros. And then free body diagram of B. We have the 10,000 Newton force down. F1 goes that way. F3 goes that way. These are all just cosines and sines of the angles for getting these force vectors right. Plus 0.5 F3, negative 0.866 F3. And then C. So for that one, we have F3 this way.
Wait, do you mean put F1 for the second one?
For which one?
The second matrix in FVDB. The free body diagram for B.
Okay. Oh, I gotcha. Yes. Yeah, you're right. This should be F1. And then that's a roller, so that the force applied by the ground is just follows the rules of a roller, just straight up. So we have negative F2, 0, negative 0.5 F3, positive 0.866 F3, plus 0 RC is equal to zeros. So now I'm going to solve this with reduced row echelon form. And all we need is F1, F2, F3, those reaction forces. We have to calculate them to get those F1, F2, F3, but those aren't going to come into anything we need. The equations 1, 2, 3, 4, 5, 6. The forces F1, F2, F3, and then RAX, RAY, RC, and then the constants. So equation 1, RAXs, we have 1. F1s, we have 0.5. F2s, we have 1. Equation 2, RAY, we have 1. F1, we have 0.866. Equation 3, F1, we have negative 0.5. Bless you. F3, we have 0.5. Equation 4, F1, we have negative 0.866. F3, we have negative 0.866. And the constant on the other side of the equation is positive 10,000. And then equation 5, F2, we have negative 1. F3, we have negative 0.5. And then equation 6, F3, we have 0.866. RC, we have 1. And so I got F1 is negative 5773.67. F2 is positive 2886.84. And F3 is negative 5773.67. And then tensions and compressions. So member 1 is in tension with a magnitude of 5773.67. Member 2 is, no, this is compression, sorry, it's negative. Number 2 is in tension because it's positive of 2886.84. And member 3 is in compression, 5773.67 newtons. And then the stress tensors, these are just in uniaxial tension and compression. So if we think of the x-axis as being along the member, they're only going to have x normal stress. And they all have a cross-sectional area of 0.0025. So I just have to divide by that. So member 1 so this is negative 5773.67 divided by 0.0025. And so that's negative 2.31 times 10 to the 6 pascals. So the stress tensor for 1, and it's going to be the same as the stress tensor for 3 because they have the same tension value, is negative 2.31 times 10 to the 6. Zeros everywhere else. And this is in pascals. And then tau max is going to be the same for both of those. So that's 0 minus negative 2.31 times 10 to the 6 divided by 2. What? 3, yes, I'm sorry. 3. Okay, and this is 1.15 times 10 to the 6 pascals. And then for member 2, so this is 2886.84 divided by 0.0025. 1.15 times 10 to the 6. And tau max is same thing again, just 0 minus, nope, this is the maximum this time. So 1.15 times 10 to the 6 minus 0 divided by 2. And so you get 0.577 times 10 to the 6 pascals. And then where do you trust these results? So this is asking about St. Venant's principle. We're making the assumption that these calculations are done by uniform forces, uniform distributed forces at the places where they're loaded. So we don't trust the stuff close to the pins. In each one of these members, so if you have a member like this, we basically want to ignore this stuff, and all the stuff that's not in a red shaded region is where we trust these results. But if what we really want is to know what's happening right at the places where it's loaded because there are stress concentrations there and stuff, we can't say anything about that. Okay. Any questions about that one?
Like not
Yeah.
on the hinge or whatever, then we can trust it.
We could trust it all the way if what was happening was really a uniform distributed load at the ends. So that's what we're always assuming. But since these are kind of concentrated forces just at those little holes, there's going to be all sorts of weird stresses right around those holes.
Yeah.
So the results that we get, is it an interesting area?
Yeah,
How do you?
that's St. Venant's principle. The things are weird around where the loads happen, but as you get a little bit away from where the loads happen, they go back to the two equipolant systems results match, but they don't match where the forces are applied. Okay, and if you did a finite element analysis where you were really calculating careful stresses, you'd get all these weird stress concentrations right at the pin and around it, but then everything would look normal again once you got away from it. Um, and then number 5. Okay, so there's no weight at the midpoint of the right beam. Oh, we can't do this yet. I don't know how this got into this set of problems, but we can't do this one yet. All we can do here is, yeah, we can do that. Okay, no, okay. We can do this. I think this is asking a question that's kind of leading us into the next topic. It's why it asks this way, because we haven't thought at all about like uh, distinguishing between the top, the middle, the bottom of a cross section. So, okay, let's go through this. So we'll call this member 1, member 2. The joints, I'll call this A, B, C. And I'm just going to, we can solve this truss just isolating B. So we have a 10,000 Newton force, and then a force F1 and a force F3.
We can just use we can just use B because we get both F1 and
Yeah, that's right. And we have two equations for those two unknowns. So let's see, we have negative 0.766 F1, negative 0.643 F1, plus positive 0.766 F3, negative 0.643 F3, plus 0, negative 10,000. So we get that F1 is equal to F3. And so 1.286 F1 is equal to negative 10,000. And so F1 and F3 are both equal to 7776.05 newtons. These have circular cross sections with given radii, 0.005. So the cross sectional area is pi times 0.005 squared. So that is 0.00785. I guess I'll leave that on. Oh, and these are both negative 7776. So the stress for both of them is negative 7776.05 divided by 0.00785. And that is negative 0.990 times 10 to the 6 pascals. Um, Okay, so now it's saying at the midpoint of member 2, what are the stress tensors at the top, bottom, and middle of this thing? So if this is a cross section of this member, so say this is the top, this is the middle, this is the bottom. There's no variation in stresses as you go around a single cross section. We're only doing calculations, for like a given cross section. So for all of these, this is just equal to negative 0.990 in megapascals. Okay, so what we've seen so far, there's not going to be any variation from different locations along the length of the member or along the cross section. What we're going to start next, we're going to start doing stresses in beams when you have transverse loads and things like that. And we're going to see that this does it starts to vary along the cross section and vary along the length of the beam. Of the 3 stress tensors from part A, I don't know, this is a very weird way to word this question, but there's no difference in the absolute values of shear stress because the stresses aren't different, but might as well calculate that. So the maximum shear stress would be 0 minus negative 0.990 divided by 2. And so that is 0.495 megapascals.
And how did you figure out that they were all equal?
Well, we just haven't even talked. I mean, that's just not something that's ever even come up before.
Oh.
So they, what we're assuming, remember, is we're doing these calculations assuming this, that what we have is this member like this, and it's being acted on by uniform distributed loads like this. Okay. And so I don't know, does it make intuitive sense that like if it's being acted on by these uniform distributed loads, there's no way any variations would come about based on how far up or down on the cross section you are. And so yeah, it isn't something that's come up yet. But now we're going to start getting into stuff like this where we have beams here, a beam here with like a force here, a force here, a force here. And when we do this, we are going to see that along a single cross section, like say this, there's going to be different stresses happening at the top of the beam than there will be at the bottom of the beam. So I think that's what I was thinking when I worded that, but it's kind of an oddly worded question, but it's just sort of a lead into like so far there's been no variation as you move along a cross section. That's about to change. Any other questions about that one?
I have a question about the free body diagram.
Mm-hmm.
So for F1, why did we do only like F1 and didn't do the other side? Is it like because it's considered as a
For where? On the free body diagram?
yeah? Number one?
Okay.
Why did we just do only F1?
There's an F3 there.
No, I mean the other side of it.
The equation.
Like you're saying, like the beam goes through the
Yeah.
pin. Why is there not another
Another-
force on the other side?
Oh, okay. Well, gotcha. I got you. Yes. This beam has no weight, and so there's nothing going on at all in that top part. Um,
Problem would be the same even if it was just that little section was absent.
yes, exactly. Yep. And there's no stresses in that part of it or anything like that. Um, I guess one way to think of it is think of isolating the top half of that beam, you know. Um, it doesn't have any forces on it except a force applied by the pin. And so if there's only one force, you know, and it has to equal 0, then that just says that part of the member isn't applying any forces to it. Any other questions? Okay, so now we're going on to stresses in beams. So in statics, we calculated internal loads in beams. But those so those start to give you a little sense of how concerned you are about a beam breaking, but it's missing some important stuff. So calculating the internal loads doesn't incorporate beam geometry, or variations in stress along a beam cross section. So that's what we're working towards, is being able to take those things into account. And we're going to start by going back over internal loads. So anybody who hasn't seen internal loads before, this will give you everything you need about that. People who've seen it with me, we're going to add one extra thing we didn't have before. So the first step is calculating internal loads in beams. Okay, so let's just start with a problem and we'll just start thinking our way through it. Let's say we have a cantilever beam. And I'm going to use a coordinate system like this. And let's say that at this end we have a point force that makes an angle of 45 degrees with the horizontal, magnitude of 1,000 newtons. And let's say that this is the new thing. Let's say that we have a couple like this of 500 Newton meters. And we want to calculate the internal load right here at the middle. So we'll say this is 0.5 meters and this is 1 meter. Okay, so remember that a couple you can think of as just like a pure moment. This would really be caused by, a couple is always really caused by two equal and opposite forces. In this case, think of the direction of that rotation. If you put your fingers in the direction of the couple vector, the rotation is like this, okay? So you can imagine that being caused by a force on the top of this beam going this way and a force on the bottom going this way, okay? Or like a screwdriver turning like this on the end. Yeah, exactly. Okay, and we want to calculate the internal loads at the red cross section. Okay, well, the first thing we have to do is calculate the external loads because those are going to come into it. So step one, we're going to calculate the external loads. So I'm going to isolate the beam. We have the 1,000 Newton force. We have the couple over here of 500. We are neglecting any weight or anything. So the only other external loads are happening at the wall. That is a fixed joint at the wall. So we know that that's going to apply a full force vector. So I'll call that R. And a full vector of couples, whatever couples we need to keep it from spinning. Well, what components of couples are necessary to keep this from spinning? The only thing that's trying to make it spin is that 500. Okay, so instead of making it a full vector, I'm just gonna do the one thing here and just call this fancy T. Okay, so that fancy T is my reaction torque. And then I have the reaction force R. And then there's going to be, so that deals with the fact that this 500 would make it barrel roll, right? But this 1,000 also is trying to make it rotate this way. So we also need a reaction couple to keep that from happening. And so I'm going to put that in like this. This is another component of couple, and I'm going to call that MR. That's my reaction moment. I guess I'll call this torque R for reaction torque. Okay, so now we have enough. I mean, remember that a fixed joint can apply enough forces and enough couples to keep the thing from rotating or accelerating. And now I've put in enough for that to happen. Any questions about that? So far it's just statics. Okay. And so now I'm going to go Newton's second law. The forces, we have Rx, Ry, plus negative, that force is 1,000. So negative 707.1, negative 707.1. That's all the forces. Couples aren't forces, so this comes out to be 0, 0. And so that reaction force is just positive 707.1, positive 707.1. And now I'm going to do the couples. I guess I'll first do it about the z-axis. So we have MR plus. So now let's think about the moment produced by this 1,000 Newton force. There's a component like that and a component like that. The horizontal component isn't going to produce any moment, but the vertical one is. So we can think of this as plus or minus a moment arm of 1 and a vertical component of 707.1. And would that force make it rotate clockwise or counterclockwise?
It would make it rotate clockwise.
Clockwise, so we want the negative. And this is equal to zeros. And so MR is equal to positive 707.1 Newton meters. Any questions about that one? You could do these with the table too.
Like we didn't.
Write out the whole table. What?
Like we didn't satisfy.
Yeah, right.
What is a 500 couple?
So now I'm doing that because that's about the x-axis. We just did it about the z-axis. So now the moment equation about the x-axis. This one's simple. All we have is fancy TR plus 500 is equal to 0. So that reaction couple is negative 500 Newton meters.
Why in the first one we have the negative 707.1? Why is it negative?
In Newton's second law or in the...
Yeah, and then with this.
I just came up with the components of this. That's a 45-degree angle with the horizontal. So cosine and sine of 45 degrees is 0.7071. Then multiply it by 1,000.
And it's negative since it's going down.
Yep, because the direction it's going, yeah.
What is DR?
T is for torque, and then R is for reaction.
Oh, that.
And so that's, so the meaning of that reaction torque is a couple, use the right hand rule. So it's a couple that's, trying to keep it from twisting along this axis. We got that it was negative. This one's positive. So in order to counteract that, it's pretty clear that it would have to be negative. And so that's what it is. So if there was no reaction couple here, this 500 would make it have an angular acceleration this way. But we know that's not the case, so the connection with the wall prevents that.
How do we calculate the moment?
The what?
The moment.
This?
Yeah, MR.
This. Okay, so on a horizontal beam like this, vertical forces can produce moments, horizontal forces can't. So the moment is going to be the moment arm times the force. Okay. And then it's going to be positive or negative based on that rotation that it would produce as clockwise or counterclockwise. So the moment arm was 1. That's the 1. Okay.
What is the info? Oh, done.
The length is 1, and it's happening at the end.
Okay, yeah. Now I see it.
And then the vertical component of the force is 707.1, so I multiplied by that. And then we thought would it make it rotate clockwise or counterclockwise? It was clockwise, so we used the negative. But of course, remember, you can write out the whole table and it'll do all those calculations for you. You just have to do some cross products and stuff.
The one is the one that makes me confused.
Okay.
Where did that come from?
Yeah, sure. Okay, so now we got that. So now we're going to go, so far we haven't done, it's not internal loads at all. It's just external loads. It's just statics. Okay, but now we're going to do the cut. And so what I'm going to do is my chosen body is going to be this half of the beam. And I'm going to ignore all of this. So we have stuff going on over here, but I'm ignoring all of that. All I'm using is the black. And let's see, what do we have? We have a force of 707.1 like that. A force of 707.1 like that. A couple of 707.1 like that. And then since it was in the negative direction, I'm going to just draw this in the negative direction and make this 500. So that's Newton meters. That's Newton meters. Okay. So that's all the stuff that we figured out on the left end of this beam.
What is your horizontal 707? The one line in the...
Yeah, that's just the components of the R force.
Oh, yeah.
And now, so for the internal loads, we have to consider the loads that are applied to the black piece by the piece of the beam that we're not considering. That's a fixed joint, so we know it's going to be a whole set of force vectors and couple vectors. And I'm going to write them like this. I'm going to use the sign convention we used in statics. So we're going to have an internal tension, an internal shear force, an internal bending moment. And then the one thing that's new is we're also going to have an internal torque that I'll denote fancy T. Okay, and we're going to calculate all of those.
Why did we include torque in statics originally when we were covering moments and shear forces and all that?
Why didn't we?
Yeah.
Because people don't usually. I'm only including it here to set us up for a little better understanding of some stresses in beams that we're going to get to later. But it's not a very common thing to have to calculate for internal loads. Okay, so we're going to go Newton's second law. So we have the force components at the left end plus T0 plus 0 negative V is equal to zeros. And so T is equal to negative 707.1. And V is equal to positive 707.1. And now we'll go to the moment equation. I'll do it first about the z-axis. So if our about point is over here at the left end, like we always did for internal loads. It just makes the math simpler. So what are the things producing moments about this red dot? Couples don't care about the about point, remember? So we still have this 707.1. The 500 is about a different axis, so I'm not going to put that in. The two 707.1 forces are happening at the about point, so I'm going to leave those out. Those don't produce a moment. And then the only other things that produce a moment are the minus v times its moment arm of 0.5, because that v would produce a clockwise moment around the about point. And then add on the m, and that's equal to 0. We figured out what v is up here, and so we can write this as 707.1 minus 353.5 plus m is equal to 0. And so that internal bending moment is negative 353.5.
Or do you ever have to do like multiple cuts like we did in statics?
Yeah.
So if there'd be like weight or something?
Yeah. Yep. We'll get into that.
And then why do we not have to like do like the thing where we like just use X instead of then we use 0.5?
Because exactly only
be
because I asked you for it at a specific point. Okay. But I do it this way in statics and here because I think it's really important to remember that what we're really doing is kind of this, like when we start doing it as functions of X, we're really doing a simple thing, you know, we're really just making a cut that is representative of all the different cuts you could make, you know? And so that's why I'm going this way from the most simple case, and then we'll build up from there. Okay, and we still need rotational Newton's second law about the x-axis.
What F equals negative 353?
0.5 times, we already figured out that V is 707.1. And so I just substituted 707.1 into this negative 0.5 V.
Right.
And that's what we get.
Yeah, but then why M equals that?
It's because it's half of 707.
Yeah, it's half of 707, exactly.
But what is the 707.1 minus the?
That's all the things that produce moments about the z-axis. So there's a couple of 707.1 positive, and that's this. Then there is the minus Vx, but our x is, we know that the x is 0.5. So we have minus 0.5 V. And then we have plus the m. And then I took what we know about V and substituted it in for V. And then just did the algebra to calculate m. .1 minus 353.5 is 353.5. Well, 353.6, but I rounded it. Okay, and now about the x-axis. So what are the things that produce moments about the x-axis? There's this 500 in the negative x direction. And then there's the fancy t, and that's all. And so the internal torque, fancy t, is equal to positive 500 Newton meters. So those are all the internal loads acting at that red line in the picture. Any questions about that?
What does fancy means? Like,
That is the So that is, so remember the meaning of all these internal loads is the loads that the ghost part of the beam that we're not considering is applying to our part of the beam. Okay, so that fancy T is a couple about the x-axis that's applied to the black part by the blue part. Okay. So, like notice if we didn't have that there, okay, we have a couple in the negative x producing, yeah, this couple in the negative x direction that wouldn't have anything counteracting it, and so this thing would have an angular acceleration. But we know that's not the case, you know, and so the thing that counteracts that is this internal load. Okay, so the next step is we normally don't want to know the internal loads just at a single point, this single red line. Normally what we want is to calculate the internal loads as a function as you move along the beam. So we normally want the internal loads as a function of x. So it represents every possible red line. You know, every red line is a separate cross section. So how are we going to do that? So we can do that. We can do it all in one free body diagram as long as every free body diagram would look qualitatively the same. You know, it would look the same except for length differences. Okay, so let's think about some of these free body diagrams that we would get if we moved this red line from where it is in the middle forward and backwards along the beam. Okay. So, okay, the first one would be, let's imagine that we're just considering a tiny little part of this beam. Okay, so we're not considering this force, we're not considering this torque, but the endpoint on the left has all the other stuff. It has the 500 Newton meters there. It has the 707.1 there, the 707.1 there, and the couple of 707.1 Newton meters. Okay, and then it would have all the internal loads. So it would have T, V, M, and then fancy T. So notice though, even though that's a really short piece we're considering, there are no differences in the loads that are shown in our free body diagram. Okay? From what we did in the example above. And, you know, we could do another piece like this, where we're excluding this piece. And we would have the 707.1, the 707.1, the torque of 500, the couple of, we have a number for that, 707.1. And then we'd have the internal loads, T, V, M, fancy T. So notice that even though one is obviously a lot longer than the other one, everything in the free body diagram looks the same. The only thing that's changing is how long our piece is, and we can represent that difference by just calling that X instead of giving it a number, So no matter where you draw that red line, the free body diagram looks the same. It is the same except that the length changes, the length of the beam. And so we're going to deal with that by just calling the length X. So we'll just call the length X and do one free body diagram that represents every possible red line. Okay, so let's go through that. So now this is like an internal loads problem that that we would have done in statics. So I'm going to do my cut.
I got a question.
Yeah.
On the when we were finding the moments, the first example that you saw on the C direction, we said that B produces a moment in the 0.5, right?
The moment arm is 0.5. Yep.
Yes. And where the 707, that's the couple.
Yes, on the left end.
All right. And why the RY, like the another 707 is pointing up? That one is not producing.
Because those are forces.
Oh, those are.
Yeah. So I'm trying to, on all my couples, I'm trying to label them Newton meters so you can see what are forces and what are couples.
Okay. So B is a couple too.
M is a couple. V is a force. So remember, so T and V are the tension, the internal tension, and the shear force.
Oh.
And then fancy T and M are the bending moment is M, and the internal torque. So the anything that's a couple is always indicated by either a double arrow if it's in a certain direction like this, or by a curved line instead of a vector. Okay. And then I'm also trying to put Newton meters on them just to, yeah. Okay, so now instead of doing the one single cut where X is fixed at 0.5, we're just going to use X as a variable and calculate these internal loads as a function of X. So the free body diagram, we're going to take a representative piece, and we're ignoring all the stuff happening over here. There's the 707.1 forces. There is the reaction moment of 707.1 Newton meters. And then there is the 500 Newton meter torque this way. So those are the external loads. And then the internal loads, we have T, V, the bending moment M, and then the internal torque, fancy T. Yep.
So for the moment, is it supposed to be one like this and the other one?
Well, you don't really have to think about it that way. I put it in here just using our sign convention. So you shouldn't draw those arrows. I mean, all we know is when you draw your internal loads, these directions should always be the same. Okay, the signs of them will come out in the math on their own. These over here, I drew them to represent the actual directions. That's why this one's going this way. But the internal loads, T, always make your T point that way, V that way, M that way, torque that way. And then, unlike before, where we said that we were only considering 0.5 meters of this beam, now we're saying we're considering a length of X of this beam. X can be anything inside the length of the beam. And we're going to calculate all these functions in terms of X. Okay, that's the only thing that we're changing now. This free body diagram looks exactly the same as it did in the earlier example. It's just that before we knew what X was, we had a number for it. Now we just have a variable. Okay, so, and again, my about point is going to be here. I'm always going to put my about point at the left for these. So Newton's second law says 707.1, 707.1 plus T0 plus 0 negative V is equal to zeros. And so T is equal to negative 707.1. V is equal to positive 707.1. And now we'll do the moment equation about the z-axis. So about the z-axis, we have the couple of positive 707.1 at the left end. And we have the couple at the right end, that's our bending moment. And then we have a clockwise moment of V times its moment arm, so that comes out as minus Vx. And remember, that one always shows up that way. And this is equal to 0. So now M is equal to Vx minus 707.1. V, we figured out above. So what we have here is that M is equal to 707.1 times X minus 707.1. Any questions about that one? And then this is rotational, Newton's second law. And then rotational Newton's second law about the x-axis. We have the 500 Newton meters in the negative x direction. the internal torque in the positive x direction. And so the internal torque is 500 Newton meters. So the only thing that varied here as a function of x was that bending moment. And this would look something like this. So if you plotted these functions out, the internal tension would look like this. It's just negative 707.1 the whole way. The shear force is just positive 707.1 the whole way. The bending moment is where you get something a little different. So that one, you start at negative 707.1. And by the time you get to x equals 1, it's at 0. So this is just a linear function. Like, those are horrible. That's better. Okay, just a linear function like that. And then for the internal torque, you just have a value of 500 the whole way. Any questions about that? Okay, so we still haven't talked about multiple bodies that need multiple cuts or distributed loads. So we'll do that. We'll get into that stuff on Wednesday. But for now, I'm just going to assign you a couple of problems doing pretty simple internal loads like this, getting used to the idea of having the internal torque in there. Anybody have any questions before we quit for today? Okay, that's it. So if you have trouble getting through any of these, feel free to bring questions on homework problems on Wednesday. I'd be happy to go through as many of those as you want, and we'll just slowly make sense out of this stuff. Okay, that's all.